Friends, we shall study today the direct method of tangent stability analysis. Over the years, efforts have been made actually to assess the tangent stability of the system by applying some direct methods. As you know actually that to assess the tangent stability of the system, one has to solve a set of differential algebraic equations, and for a large system the number of equations are large in number and it is quite a time consuming process. Even if we resort to dynamic equivalents, right, the dimension of the model is quite large. Here we will concentrate upon one approach which is known as the tangent energy function approach. Tangent energy function approach. In direct methods, when we try to determine the stability, one can assess the stability of the system without explicitly solving the system of differential equations. Or we can say that we can partly avoid the solution of differential equations. We may have to solve the differential equations for a short interval. For example, as you know that if you take a single machine infinite bus system, then for this we can apply the equilibrium criteria of stability to assess the stability of the system. However, to find out the critical clearing time, we do have to integrate the equations from initial operating condition up to the fault clearing time, because we know that if we obtain for a given system the critical clearing angle, then we have to find out corresponding critical clearing time. Okay? And therefore, we may have to integrate this differential equation from initial operating condition up to the critical clearing time. Okay? It means actually we may not have to integrate the differential equation or solve the equations for the complete time period, and in that case we are partly solving the differential equation for the part of the period. Okay. Now, in direct methods, in fact, they are mostly at the research level, and as yet actually the application in practical large system is not reported, because in practical large systems, as we will see that when you try to apply the direct methods, there are some problems. Now, to understand the basic concept or basic philosophy of applying the direct methods, we make use of a simple rolling ball analogy. In this rolling ball analogy, let us say a physical system where you have a bowl. This is a bowl. This bowl has uneven or non-uniform rim. Okay. Here is a ball, a small ball which is lying here in this ball. Okay. Now, the ball occupies this lowest position in the bowl, and this position is called the stable equilibrium point. Okay. Now, when this ball is perturbed, that is said that we apply some force for a short time, so that this ball is perturbed, and when you perturb, right, you are injecting some kinetic energy to this ball. Okay. Therefore, this ball will roll inside this surface of this bowl. It will roll along some path. The path along which it rolls will depend upon the direction in which the disturbance is applied, right. Now, if suppose the kinetic energy injected is large enough, so that the ball comes right up to the rim, right, and it crosses over this rim, right, then we say that the system is unstable, because once it crosses, it enters into the unstable region and it cannot return back to the stable operating condition. Okay. But suppose if the kinetic energy injected is such that it climbs a certain height in the ball and returns back, right, then the system is stable. Okay. Therefore, here if you see here that for the stability of this ball stability of this ball in this bowl, right, there are two important points to be noted. One is the kinetic energy injected, one is the initial kinetic energy which is injected to the ball. Okay. Second is the height of the rim at the crossing point, height of the rim at the crossing point. Then the location of the crossing point depends on the direction of the initial motion. The location of the crossing point depends on the direction of the initial motion. It means when you give some disturbance, right, then the ball is going to move over a certain trajectory inside the bowl, okay, and depending upon the direction in which it is made to move, right, the height is going to be different, because I have assumed that the rim is non-uniform, uneven. And therefore, if I want to find out whether this ball which is lying inside the bowl, right, forms a stable system, right, I should know what is the kinetic energy which is injected to the system and what is the height of the rim. Now, as you know actually that suppose when the ball is perturbed, right, as it moves along, then it acquires potential energy which depends upon the position of the ball, or actually height of the ball with respect to the stable equilibrium point. This is the potential energy, and when it is moving, it loses kinetic energy. Now, suppose when it just comes to the particular point on the rim and the speed of this speed of the ball becomes 0, right. It means at this particular point the ball has acquired the potential energy only, it has a total potential energy, it does not have kinetic energy. Now, in case the ball comes up to this particular point and it does not have any kinetic energy, then the forces will act on this ball to bring back to the stable equilibrium point. And therefore, if I want to assess the stability, I must find out what is the energy, what is the potential energy which the system can provide, or we can say another way that what is the capability of the system to absorb the energy imparted to the ball, and the energy imparted to the ball depends upon what is the maximum potential energy which it can acquire. Therefore, from the stability point of view, we can consider like this, that I can define an energy function. And let us say the energy which this system acquires, is denoted by a symbol V. We will denote this energy by a symbol V, or V is a energy function, right. Now, let us denote the XCL as the state of the system at fault clearing. When I say state of the system means for a single machine infinite bus system, the state can be described by the two state variables. One is delta, another is omega, speed and angular change. Therefore, this delta and omega, these two are the state variables for a single machine infinite bus system. Now, if I know what is the state of the system at the fault clearing time, right, that I call this XCL as the state of the system at fault clearing time, and let us say that V, which is a function of the state of the system, as VCL, V at XCL. Okay. I will denote this as a transient energy function, is called XCL. Now, we find out a critical energy. VCR denote the critical energy, and the difference, that is the critical energy minus the energy at fault clearing time, that is V, which is function of XCL, right. This difference is the transient energy margin, a very simple concept, right. Now, if I again look back at this rolling ball analogy, right, the critical energy is the energy corresponding to the potential energy which this system can provide, right, at the crossing point. Okay. And since actually the disturbance can make this ball to move in different directions, right, therefore, critical energy is different for different directions of motion, right. Now, when I look actually now a practical power system, then we can apply this analogy to a practical power system also. How? That suppose the system is operating in the steady state condition and a fault occurs in the system. Okay. Now, the moment the fault occurs, during this fault on period, right, the rotors of the synchronous machines accelerate, okay, and acquire some kinetic energy. Similarly, the angular position of the rotors also change. Therefore, we can say that the machines in the system acquire some kinetic energy, the total kinetic energy, plus some potential energy. This potential energy depends upon the angular position of this rotor with respect to the stable operating angular positions. Okay. Now, if the system is capable of absorbing the kinetic energy which you have injected into it, right, then the system will be stable. If the system cannot absorb that kinetic energy completely, right, then system becomes unstable. It is a very simple concept. Now, here we will first concentrate upon the application of this transient energy function approach to a single machine infinite bus system, and we will also show that the equilibrium criteria which we are very much familiar, right, can also be interpreted in terms of energy functions. Therefore, now our first step is to define a tangent energy function. How we define the tangent energy function? Now, to define the tangent energy function, we start with a simple system, and that is the single machine infinite bus system. That is, we will find out the energy function for a single machine infinite bus. Okay. Once we understand the basic concepts, we will extend this concept to a multi machine system. The basic swing equation of a single machine infinite bus system, I shall write down in this form m d omega by dt equal to P m minus P e. Another equation I am writing here is d delta by dt equal to omega. I am writing in this form, which is slightly it appears slightly different from what we have been using. Now, here this omega is the deviation of speed from the synchronous speed. Therefore, instead of writing delta omega, I can write down simply omega for the sake of simplicity, that this omega is the speed deviation. Okay. Now, here I am not stating that the speed deviation is in per unit or speed deviation actually in radians per second. Okay. It will, the value of this if you want to use in per unit, then appropriately the m has to be chosen, right. Now, the energy functions are always computed for post fault system, that whenever we compute the energy function or define energy function, right, the energy functions are always constituted for post fault system. Now, for the post fault system, let us define that P e is equal to P max 3 sin delta. Here actually we the 3 power angle characteristic will define that P e 1 equal to P max 1 sin delta, P e 2 equal to P max 2 sin delta, and for post fault condition it is P max 3 sin delta. Therefore, the in this equation P e is equal to P max sin delta. Okay. Now, what we do here is that using these equations, these two equations, this equation and this equation, okay, we can write down here dt can be written as m d omega divided by P m minus P. Let us suppose I write down here dt. I just consider actually the small perturbations, and let us say that this d omega and dt can be separated, right. So, I can write dt equal to m d omega by P m minus. Let us write down this denominator in the form of a function. I can write down this as m d omega by a function which is basically a function of delta, f delta. For the second equation, we can write down dt equal to d delta by omega. If I take the second equation, dt equal to d delta by omega. Now, we can write down here m d omega divided by f delta equal to d delta by omega, because dt equal to this, dt equal to this, they are meant equal. Okay. Or we can say here m omega d omega equal to f delta d delta. Okay. Now, you integrate both sides of this equation, then we can write down here as m integral of omega d omega equal to integral of f delta d delta, which can be written as 1 by 2 m omega square equal to, I will just say integral of f delta d delta. Here at any instant of time, the 1 by 2 m omega square is equal to integral of f delta d delta, because these are equal. However, now so far omega is finite, this quantity is finite, right, and therefore, this is also going to be finite. The energy function is defined, we use this definition V omega delta is defined as 1 by 2 m omega square minus integral of f delta d delta. This is what is the basic definition of energy function here. Now, we can identify that this part of this energy function represents the kinetic energy. Therefore, we call this as V k E, while this portion or this part of the energy function, right, depends upon the angular position delta. It is a function of delta only, and therefore, this is called, this part of the energy function is called V p E, and we denote specially, or we put delta along with it. So that this is a potential energy and it depends upon delta. Now, here if you clearly, you can say, try to write down the expression for V p delta, right, then this V p delta can be considered to be, because in this equation suppose you see V p delta is basically the negative of integral of f delta d delta, right. Therefore, I can write down for this single machine infinite bus system the value of V p delta, V p E delta can be written as negative of integral of f delta d delta. Okay. What is your f delta? F delta we have denoted as P m minus P max 3 sin delta. But now, here you can put here is minus P m minus P max 3 sin delta d delta. Is it okay? Or its value you can write down as, if you integrate with respect to, integrating with respect to delta, it can be written as minus P m delta. Now, when you integrate this quantity, sin delta will have a minus cos delta, that is integral of sin delta is minus cos delta, okay. And therefore, this continues to be minus P max 3 cos delta. Okay. Now, here we do one interesting coordinate transformation, that is we would like to can say express this potential energy such that for the post fault stable equilibrium point its value is 0. That is, we want to express this V p delta, that is the potential energy, in such a way so that its value is 0 for stable post fault stable equilibrium point. Now, suppose in this expression, if I integrate this equation, if I integrate and you put the limits, let us say that I will put the limits here from delta s to some angle delta. And let us say that integration is performed, so that we do it from some angle delta s to delta. Okay. Then we can write down this as V p e is now function of delta and delta s. Okay. This can be written as minus p m delta minus delta s minus p max 3 cos of delta minus cos of delta. That is, this expression we have written was in general. I have not put any initial and final limits. Here what we are doing is that we want to can say have the coordinate system in such a fashion, so that this V p is 0 for post fault stable equilibrium point. Now, for example, in this equation, if I put delta equal to delta s, if I substitute in this equation delta equal to delta s, then this quantity is 0, right. Yes.
If delta equal to delta s, then V p delta s equal to minus p max 3, because there is a
See, I am putting delta equal to delta s, so that this term is 0 and this term is also 0. Cos delta s minus cos delta s becomes 0. That is, instead of making our coordinate system such that the potential energy is measured for delta equal to delta naught or delta equal to 0, we would like to have the coordinate system in such a fashion, so that at the post fault stable equilibrium point the potential energy is 0, right. Further, we will show that, so that this the total energy function, because when I talk about the energy function, this is also called the transient energy function, which is sum of kinetic energy and potential energy, right. For the post fault condition, we will show that this quantity is constant. For the post fault system, right, the transient energy function is a constant term. Now, to show this thing, we can proceed in a simple fashion like this, that you have your basic equation m times d2 delta by dt2 equal to P m minus P e. Okay. Now, because the way we have defined actually the potential energy, we can write down here that d negative of V p e d delta is equal to P m, not P max, P m minus P e. Because when you have seen here, actually when we define this Vp, you just look at this equation. The definition of Vp is Vp delta is equal to minus integral of V f delta d delta. Okay. Therefore, if I take the negative and take the d by d delta of this quantity, then it is equal to f delta. Okay. That is, I can say now here that in this equation we can write down m d2 delta by dt2 can be written as minus d by d delta of Vp. Okay. This is by definition. You multiply both sides of this equation by d delta by dt. That is, you write down this as m times d2 delta by dt2 d delta by dt equal to minus d by d delta V p e into d delta by dt. Okay. Now, this term can be identified. You can then take this side on this side. This can be identified as m by 2. This can be identified as d by dt of m by 2 d delta by dt whole square plus what will the quantity here? Vp d by dt, the delta you can take it out, and therefore d by dt is here plus Vp, and this quantity is 0. That is, you take this equation, okay, and you write in this form. Therefore, if you take the derivative of this expression, you will get the upper equation, right, and therefore, this term is 0. The meaning of this is that the expression within the bracket is constant, right. Derivative of this complete expression becoming 0 means this term which is within the brackets is a constant term, or we can say here that 1 by 2 m, what is d delta by dt? Omega square plus Vp is constant. Okay. Or I can say here that the energy function which has two components Vke plus Vpe equal to a constant. Now, this is very important thing actually. Physically, I want to just explain that when the system is disturbed, okay, and let us say that the fault is cleared, you are looking for the post fault system, energy function is constituted for a post fault system, right. Then in the post fault system, whatsoever is the energy which is injected, right, when the system is in motion, what happens is that the total energy is apportioned between Vke and Vpe, right. Therefore, suppose a situation comes where Vke becomes 0, then this total energy will become potential energy only, right, but this total remains same. Now, here I want to just tell you one more point here. There is any system you will find stable equilibrium point, another is the unstable equilibrium point, stable and unstable equilibrium points. For a single machine infinite bus system, right, under the post fault condition, we can find out the stable equilibrium point by equating this term P m minus P max 3 sin delta equal to 0, right. So, that the stable equilibrium point, that is delta S, is equal to sin inverse P m divided by P max 3. This is the stable equilibrium point. Now, we have unstable equilibrium point. There will be two unstable equilibrium points which will satisfy this equation. One unstable equilibrium point I will denote as delta U. This will be pi minus delta S. Another will be, we will denote as delta U, say cap, as minus pi minus delta S. That is, you substitute in this equation delta U equal to pi minus delta S, this equation is going to be satisfied. Similarly, you substitute delta U hat as minus pi minus delta S, then also this equation is going to be satisfied. Now, these two points are called unstable equilibrium point, okay. And the critical energy that is VCR, which we call, right, is the potential energy at this unstable equilibrium point, right. Now, just to demonstrate how we can plot actually we plot a graph for potential energy and show actually that how the potential energy varies as you vary the angle delta. Now, to plot this graph, let us start like this. On this axis we will put delta, and here I am putting V P E. This is the potential energy. As per our definition of the energy function, the potential energy is 0 at delta equal to delta S. Let us say this point is delta S, okay. Now, and let us say that this point is pi minus delta S, that is delta U. When I say that there is another unstable equilibrium point, it is on this side, that is minus pi minus delta S. If we now plot the potential energy as a function of delta, then this plot will come something like this. I will use a different color. Let me use of this form. Therefore, this is the value of Vp, this is the value of Vp at delta U, or this quantity is V P E at delta U hat, okay. This is the value of Vp at delta U, and at delta S, which is the stable equilibrium point, this quantity is 0. Now, if the total energy is equal to some quantity, let us say E, some quantity say E, and let us say that this is the delta, that is the angle at fault clearing, that is the fault clearing angle. Then at this point this represents the potential energy, we can call it V P E, and if total energy is say E, I am using the word say total energy E. E is the total energy, then this portion will be your V K E. At this stable equilibrium point, the total energy will become now how much? 0. V P is 0, and the total, if E is constant, therefore, at this point it is going to be only kinetic energy. That the stable equilibrium point, when the system comes, actually it has a large maximum speed, delta omega, the speed deviation is large at the stable equilibrium point, that is why it keeps on oscillating, right. Now, suppose the total energy which is associated in the post fault system, which I told you that this is constant, and if this is less than this V P corresponding to delta U, my system is stable. Okay. Conceptually, the subject is very simple here, that if we can find out the critical energy, and the critical energy in this particular system is corresponding to is the potential energy corresponding to the unstable equilibrium point, and if I know what is the total energy which is injected into the system, right, and this total energy remains constant. This total energy has two parts, the potential and kinetic, and actually as the system moves, right, you will find actually that the total energy is a portion between the potential energy and kinetic energy, right, and therefore condition for stability is that the potential energy at unstable equilibrium point, which is the critical energy, is more than the total energy injected, or actually total kinetic energy which is injected, which at any other angle is actually a portion between the two parts. Therefore, whenever if you want to find out whether the system is stable or not, right, what is to be done is that one has to find out what is the critical energy, and one has to also find out what is the total energy injected into the system, right. And if we can find out actually critical energy without actually solving the set of differential equations, right, then to find out the total kinetic energy injected, one may have to integrate the equations from t equal to 0 up to the time t when the fault is clear, only for a short time. During fault condition we may have to integrate to find out what is the total kinetic energy injected. Now, we will establish here the relationship between the equilibrium criteria of stability and the tangent energy function approach for assessing the tangent stability. We will establish that equilibrium criteria of stability is same as the tangent energy function approach. Right. This TEF, as I have just told you, the tangent energy function is function of delta and omega, and it has two components, the kinetic energy and potential energy. Now, to illustrate this, that we consider the same machine infinite burst system, and this is the diagram which is drawn, and it shows the three power angle characteristics, the pre-fault, this is the post-fault, this is the faulted one. Okay. The peak value of this post-fault power angle characteristic is shown as P max 3. The peak value of during the fault is P max 2. okay, and the mechanical input is Pm. Okay. This is, I think we are all very well familiar with this. Now, let us say that we are operating at initially at an angle delta naught on the pre-fault power angle characteristic, and the fault occurs and which drive the system on this post fault power angle curve, and let us say that fault is cleared at delta equal to delta CL. So, that now you shift your operating point from faulted curve to post fault curve and you move on this. In this diagram we can see that the unstable equilibrium point is shown here, where the post fault power angle characteristic intersect with Pm, that is, this is your unstable equilibrium point, its value is equal to pi minus delta S, and delta S, the stable equilibrium point, is the intersection of Pm with post fault power angle characteristic. Okay. Now, to establish this, what we do is we have to look for the three areas. The area, this is area A1, okay. This is the second area A2. This area A1 is actually the area which represents the kinetic energy. I will explain. This represents the kinetic energy. We will show that it represents kinetic energy. This area A2, right, is a part of the potential energy, okay, and our stability criteria is that A2 should be greater than A1, right. Stability criteria is A2 should be greater than A1. Now, here when I try to apply the tangent energy function approach, we look at this third area also, this area A3. This area A3 is bounded by the post fault power angle curve, mechanical input line, and the angle delta S and delta CL. That is, this area is A3. Okay. Therefore, if our stability criteria is that A2 should be greater than A1, this is our equilibrium criteria of stability. Now, what you do is that you add this area A3 to both sides of this equation. So, that I can say A2 plus A3 it does not change, because I am adding the area A3 to both sides of this equation. Therefore, A2 plus A3, if it is greater than A1 plus A3, right, then my system is stable. Now, this A1 plus A3, if you look here, this area when you are at this point delta CL, right, this area which is A1, it represents the kinetic energy, that is 1 by 2 m omega square, where omega is the speed corresponding to delta CL, while this A2 represents the potential energy VPE corresponding to delta CL. Okay. And this sum must be equal to this total. Okay. In fact, this area, there is A2 plus A3, this represents the critical energy. We can establish now by obtaining the or by deriving the expression for A1, A2 and A3, and then we will show that A2 plus A3 represents the critical energy, that is the potential energy corresponding to delta U, and A1 plus A3 represent the tangent energy at delta CL, which has two components, one is the critical energy, one is the potential energy, right. Now, this can be easily proved I will just do partly, because you can just write the expression for these 3 areas A1. Now, A1 you can write down the, let us just write down what is A1. A1 is you can find out A1 by integrating this expression, that is P m minus P max to sin delta from delta naught to delta CL d delta. Okay. Now, here what we do here is this quantity is equal to m, this quantity is basically your m times d omega by dt. During the, this is what we are doing is we are trying to find out the area, and this represents the integration over the angle delta CL to, or delta not to delta CL, right, that is during the faulted condition, and this expression is always equal to m times d omega by dt, okay, and you put this as d this is what we are replacing here. This is replaced by this is d delta. Now d delta by this d delta by dt is equal to omega as per our definition. So, that I can write down this expression as m omega d omega, d delta is replaced by omega into dt, and this quantity is your 1 by 2 m omega square. Now, here you are integrating from 0 to omega CL, right, because at delta equal to delta naught, the speed deviation delta omega CL or omega is 0, right. Therefore, this quantity can be written as, therefore, A1 represents the kinetic energy, that is you can say that this is the kinetic energy imparted to the system. Similarly, you write down A2 and A3 and establish that the A2 plus A3 is actually the potential energy corresponding to the unstable equilibrium point delta U, right, and the tangent energy corresponding to this fault clearing angle delta CL is this kinetic energy plus the potential energy, which is equal to delta, which is equal to or which is proportional to your area A3. Therefore, I suggest you to write the expression for A2, A3 and establish that A1 plus A3 represents the tangent energy function, right, which is corresponding to the clearing angle delta CL, and the remaining the expression that is A2 plus A3 represent the critical energy. Okay. With this, let me summarize that today what we have done is that we have studied the basic concepts of direct method of tangent stability analysis. We have devoted our time to tangent energy function approach, and the studies are confined to a single machine infinite bus system. Thank you.